For thousands of years before telescopes, before satellites, before any of the tools we now take for granted, human beings looked up at the night sky and felt something stir inside them. Not just wonder, though there was plenty of that, but a hunger to understand. Sitting around fires beneath a canopy of stars, they watched the moon wax and wane, tracked the sun's daily arc, and noticed that certain stars returned with the seasons like reliable old friends. They didn't know what stars were made of. They didn't know how big the Earth was, or whether they were standing still or hurtling through space. But they sensed something important. The sky was telling a story, and they were determined to read it. Night after night, generation after generation, the observations accumulated. Patterns emerged. The stars swept across the sky in great arcs. The moon kept its own rhythm. The whole heavens seemed to rotate like an enormous wheel. And to the people standing on solid ground, the conclusion felt inescapable. The earth was still and the sky was moving. Every dawn confirmed it. Every sunset seemed to prove it again. And yet, tucked inside that familiar daily motion was a question that would take centuries to answer. Were the stars truly circling the earth? Or was the earth itself moving through the cosmos, too slowly for any of us to feel? Asking that question turned out to be the beginning of science itself. Across the ancient world, civilizations started doing something more than just watching. They started recording. Mesopotamian astronomers pressed observations into clay tablets. Egyptian priests tracked the star Sirius to predict the Nile's flooding. Chinese scholars documented comets and eclipses in careful sequence. The Maya, working without any contact with the old world, built observatories and developed calendars of stunning precision. These weren't separate projects. They were the same project, running in parallel across continents and centuries. Humanity was trying to discover the hidden order behind the heavens. But even as that knowledge grew, the central question remained wide open. What was actually moving? By the ancient world, two competing pictures of the cosmos had taken shape. The first, and by far the most popular, placed Earth at the center of everything, with the sun, moon, planets, and stars all circling it. It felt obvious. It matched what your eyes told you every day of your life. But a handful of thinkers kept poking at it. What if those appearances were deceiving? What if Earth was the thing doing the moving, and we were simply too embedded in that motion to feel it? It was a radical suggestion, one that challenged not just astronomy, but philosophy, tradition, and humanity's entire sense of its own importance. And so the debate continued, rolling forward through the centuries like a stone gathering speed, until in the 16th century it finally broke loose. In 1543, a Polish astronomer named Nicholas Copernicus published a model of the solar system that placed the sun, not the Earth, at the center. In his vision, Earth became a planet, one of several, traveling through space alongside the others. It was a staggering demotion. But something remarkable happened when you accepted his premise. The strange wandering paths of the planets suddenly started to make sense. Their loops and zigzags across the sky weren't caused by elaborate celestial machinery. They were an optical illusion, the result of one moving planet observing another from a shifting vantage point. The cosmos, seen through Copernicus's eyes, became simpler and stranger at the same time. But an idea, no matter how elegant, still needs evidence. And soon a new invention would change everything. That evidence began arriving in 1609 when an Italian mathematician named Galileo Galilei pointed a recently invented instrument at the sky. The telescope was crude by modern standards, but what it revealed was extraordinary. He found mountains on the moon, proving the heavens weren't the perfect, untouched realm that tradition insisted upon. He spotted 4 moons orbiting Jupiter, which demolished the claim that everything in the cosmos revolved around Earth. He observed Venus going through phases, just as our moon does, which only made sense if Venus was circling the sun. Everywhere his telescope turned, the universe appeared to be confirming Copernicus. For the first time, observation was beginning to triumph over assumption. But the world wasn't ready to let go of the old universe just yet. What happened next says as much about human nature as it does about science. The evidence mounted, but powerful institutions had spent centuries building their understanding of the universe around Earth's central motionless position. To question that model felt to many like questioning the foundations of civilization itself. In 1633, Galileo was summoned before the Inquisition and forced to publicly recant his support for the idea that Earth moved around the Sun. He complied. Tradition for the moment held. But the observations didn't disappear. Jupiter's moons kept orbiting. Venus kept cycling through its phases. Nature, it turns out, doesn't adjust its behavior based on what authorities find convenient. The evidence was still there, waiting. And a new generation of scientists was already asking the next question. If Earth moves through space, how do we prove it directly? Skeptics had a fair point. Even granting Copernicus and Galileo everything they claimed, there was a challenge that lingered. If Earth really was traveling around the Sun, our position in space should change throughout the year. And if our position changed, nearby stars should appear to shift very slightly against the background of more distant ones. The way a nearby tree seems to move against distant hills when you shift your head. This effect is called stellar parallax, and finding it would be direct, measurable proof that Earth was moving. Astronomers hunted for it for nearly 200 years. The problem was that it was extraordinarily tiny, far smaller than anyone had initially expected. Finally, in 1838, a German astronomer named Friedrich Bessel found it. The shift was almost impossibly small, far less than the width of a human hair seen from miles away. But it was there, and it was real. Earth moved. The universe was far larger than anyone had dreamed. And yet almost all of this evidence still lived in telescopes and mathematics. What the world was still missing was something you could simply watch, with your own eyes, in an ordinary room. That moment was coming. It arrived in 1851 in Paris. A French physicist named Léon Foucault walked into the Panthéon, the enormous domed mausoleum where France buries its great minds, carrying a large brass sphere and a wire nearly 200 feet long. He suspended the sphere from the dome, set it swinging, and stepped back. At first, nothing seemed unusual. The pendulum moved back and forth in a straight line, steady and quiet. But over the following minutes and hours, something remarkable became visible to everyone in the room. The plane of the pendulum's swing was slowly rotating, turning it like the hand of an enormous clock, 1 degree at a time. The crowd was watching the Earth rotate. No telescope, no equations. Just a swinging weight and a turning world. It was one of the most elegant experiments ever devised, and the question it immediately raised was just as fascinating. If the pendulum is attached to the Earth, why doesn't it simply spin along with it? The answer lies in one of the most fundamental ideas in all of physics. More than 300 years before the pendulum experiment, Isaac Newton described it in his first law of motion. An object in motion stays in motion in a straight line unless something pushes it off course. This is inertia. Once set swinging, the pendulum has no reason to turn left, no reason to turn right. It simply keeps doing what nature prefers, maintaining its original plane of motion through space. The floor beneath it, on the other hand, is attached to the Earth, and the Earth is rotating. Imagine drawing a perfectly straight line in the air while standing on a slowly spinning carousel. To someone on the carousel with you, that line would appear to drift sideways over time, but the line itself never moved. The platform did. That is exactly what Foucault's audience was witnessing. The pendulum held its course. The Earth slipped quietly beneath it. And what appeared to be a rotating pendulum was really a rotating planet, made visible at last. What made the experiment even more compelling was that the effect wasn't the same everywhere on Earth, and the differences were perfectly predictable. At the North Pole, Earth's rotation is directly beneath you, and a Foucault pendulum there would complete a full circle in exactly 24 hours. Move toward the equator, and the apparent rotation of the pendulum slows down. At the equator itself, it appears to stop entirely. Not because Earth has stopped turning, but because of how the geometry of Earth's rotation changes what an observer standing there would perceive. Cross into the southern hemisphere, and the pendulum reverses direction. Scientists could calculate the exact rate for any latitude on the planet, And when they tested those predictions in Paris, in Sydney, in New York, and in Buenos Aires, the pendulums behaved exactly as expected. Different cities, different latitudes, one consistent explanation: a rotating Earth. The pendulum wasn't just proving motion, it was revealing the hidden geometry of the planet itself. But zoom out for a moment, and that pendulum fits into something much larger. Long before Foucault, long before Newton, long before Copernicus, human beings had been doing exactly this: observing carefully, finding patterns, and using what they found to navigate and survive. The Egyptians used the rising of Sirius to anticipate the Nile's flood. Babylonian astronomers built records of planetary motion that spanned generations. Polynesian navigators crossed thousands of miles of open ocean, using nothing but stars, swells, winds, and memory. These weren't primitive fumbles toward real science. They were real science, carried out with the tools available and the same fundamental instinct. Pay attention, find the pattern, follow where it leads. The Foucault pendulum stands in that same tradition. A simple observation leading to a profound realization. A reminder that some of humanity's greatest discoveries begin with nothing more than the willingness to watch. And as the centuries of discovery stacked up, an extraordinary pattern revealed itself. The same physics that governed a swinging pendulum in a Paris cathedral also governed the orbit of Neptune. The force holding the moon in its path around Earth was the same force holding distant galaxies together. The universe, for all its staggering scale and complexity, appeared to operate according to a single coherent set of laws. Not one set for Earth and another for the stars, but one framework connecting everything. Once humanity began grasping that, everything changed. Navigation became more precise. Timekeeping became more accurate. Technology advanced in ways no single generation could have predicted. Space exploration became possible. Each generation inherited the knowledge of the one before it and pushed the frontier a little further, because they were all, without knowing it, working on the same problem. The Foucault pendulum did more than demonstrate Earth's rotation. It changed the way people thought about evidence. For most of history, the great truths about the cosmos were locked behind specialized knowledge, the kind that required training, instruments, and a willingness to trust experts you'd never meet. Foucault cracked that door open. You didn't need advanced training. You didn't need a telescope. You didn't need to trust an authority. You could stand in the room, watch the pendulum swing, and observe the evidence for yourself. That idea, observation, measurement, verification, became one of the foundations of modern science. From observatories to satellites, science advances when ideas are tested against reality. And perhaps that is the pendulum's greatest lesson. Knowledge is not built on belief alone. It is built on curiosity, investigation, and the willingness to follow the evidence wherever it leads. Today we know something our ancestors could scarcely have imagined. The Earth is not the center of the universe. It is not fixed. It is not isolated. It is a small world orbiting an ordinary star, traveling through a galaxy containing hundreds of billions of others. And that galaxy is only one among billions more. And yet somehow, from this tiny world, conscious beings emerged who could figure that out. The same atoms forged inside ancient stars now sit in the neurons firing as you watch this video. The same laws that govern galaxies governed the pendulum swinging in the Pantheon on a winter day in 1851. We are not observers of the universe from the outside, we are part of it, a part that somehow became curious about the whole. And that may be the most extraordinary fact of all. The story didn't end with Foucault. In many ways, it was only the beginning. We have walked on the moon, sent robotic explorers to Mars, photographed black holes, detected gravitational waves, ripples in the fabric of space-time itself, using instruments sensitive enough to measure a distortion smaller than a proton. And yet, for every mystery we've solved, new ones have opened up. What is dark matter? What is driving the accelerating expansion of the universe? Is there life elsewhere? How did consciousness arise? What, if anything, came before the Big Bang? Every answer has been a door into a larger room. The frontier has moved farther away, but it has never disappeared. The universe still calls to us, still challenges us, still invites us to explore. Discovery is not a destination, it is a way of life. And now the story arrives somewhere unexpected. Here, with you. For thousands of years, the chain of discovery has passed from one generation to the next, each one inheriting what came before, each one adding something new. You are part of that chain. You don't need a laboratory or an observatory. The spirit of discovery begins with something much simpler: the willingness to ask what if, to follow a question wherever it leads, to sit with uncertainty long enough for understanding to arrive. Every breakthrough in human history began with someone who noticed something and refused to look away. The first person who tracked the stars, the astronomer who dared to move the sun to the center, the physicist who hung a pendulum from a cathedral ceiling. They all started the same way, curious and paying attention. The pendulum still hangs in the Pantheon. It still swings hour after hour, tracing its slow circle on the floor, revealing with perfect patience the rotation of the Earth beneath it. More than 170 years after Foucault first set it in motion, visitors still stop and stare, sometimes for a long time, trying to let the reality of it settle in. Not just that the Earth is turning, they knew that walking in the door, but that you can see it, right here, right now, without a single piece of mathematics. The world is spinning, and you can watch it happen. That's what discovery feels like. Not always an explosion, often just a quiet shift in how you see something that was in front of you all along. The pendulum continues its silent swing. The Earth continues to turn. The stars continue to shine. And somewhere, right now, another question is waiting to be asked. So look up, stay curious, keep asking why. The greatest chapters are still ahead. Stay lucid.